Welcome back. In this section, we'll be talking about real zeros of polynomial functions. If you're thinking back to 5.1 or even the previous section, if you were graphing a polynomial function or solving a polynomial inequality, you would need to know where are the x-intercepts for that polynomial function. And that means that if it's not already a factored polynomial, you'll need to be able to factor it. One thing that we'll just state outright is that the connection exists between division and factoring, that there really are essentially the same thing. If you had some sort of a function f of x and you had something that you divided f of x by, you would find a quotient and a remainder. And you could write f of x as the quotient times whatever you were dividing by plus whatever the remainder is. But if something that you were dividing by turned out to be a factor, then that remainder would be 0, which means that f of x really could be just written as your divisor times whatever the quotient is. So that's sort of the one idea here, that when we have something that actually is a factor, to do the factoring out, we'll carry it out by doing division, and whatever the quotient is, that'll be what's left over after we've factored our term out. So there's a couple of things that we'll need to think about here. One would be, how do we decide if something's a factor or not, and where are we getting these hypothetical factors from? So the first part, the testing of a factor, or testing if something is a factor or not, we have two ways that we can do it. There's the obvious way, which is if you wanted to know if x minus c is a factor, you could take your polynomial and divide it by x minus c and see if the remainder is 0. But that means you actually have to carry out division. As it turns out, there's an easier way to find out what the remainder is without doing division, and that's the remainder theorem. The remainder theorem tells us that if you have a polynomial function and you are interested in dividing that polynomial function by x minus c and finding out what the remainder is, well, as it turns out, that would be the same thing as just evaluating your function at c. So, for example, if you were to take f of x and divide it by x minus 2, the remainder that you would get should be whatever the value of f of 2 is. If you were to take f of x and divide it by x plus 7, the remainder should be whatever the value you get at f of negative 7. So we don't actually have to do the division to find out what the remainder is. We just need to evaluate our function at that value of x. So as an example here, I've got a polynomial f of x, and I'm going to demonstrate this remainder theorem in action. First off, finding the remainder when we divide it by x minus 1. So f of x, that is 1x to the 4, 0x cubed minus 3x squared minus 2x plus 1. And I'm dividing by x minus 1, so I'll use a positive 1 here. If you're a little bit hazy on synthetic division, and this is a mystery to you right now, this would be a good point to pause the video and go back and have a look at the synthetic division video, because we are going to be making heavy use of synthetic division in this section. So I've carried out my synthetic division as usual, bringing down my first coefficient, multiplying and adding, and carrying out my steps as always. And I find that that last number of negative 3, that should be my remainder. And if I wanted to mention my quotient here, the quotient should be x cubed plus x squared minus 2x minus 4. Okay, so I found my remainder was negative 3, and I did that by actually dividing. But I can confirm that that's the same thing as just taking your polynomial and evaluating it at 1. If you were to put 1 in for x, That's also equal to negative 3. And one thing to notice here is, just as far as time is concerned, evaluating a function at a single value, even though synthetic division is pretty fast, it's not as fast as just evaluating a function at a single value. So if you have your choice between doing division versus using the remainder theorem might be a faster way to do things. Of course, it's totally fine if you want to confirm that something's a factor or not by actually doing division. You certainly can, but you don't have to. So that connects with the idea from before. We said that if you had something that was a factor, then it would divide in and have no remainder. But of course, you know that if x minus c is a factor, if it leaves no remainder, then that means f of c should be 0. And that's sort of the connection here with the remainder theorem. You know that f of c, that's the remainder that you get when you divide f of x, dividing it by x minus c. And if x minus c is a factor, then the remainder would be 0. And if the remainder is 0, then f of c should be 0 as well. That's our idea here, that if you're looking to tell if something's a factor, it really just boils down to it's the places where, when you evaluate the function, it gives you a y value of 0. And that's our factor theorem. So if you're interested in this question, f of x, which of these happen to be factors, instead of doing division 3 times in a row, we would just need to evaluate. What's f of 3? Is it 0 or not? What's f of negative 2? Is it 0 or not? What's f of 1? Is it 0 or not? One thing to notice here is if x minus 3 is a factor, that would give you the x-intercept of 3. That's why I'm using positive 3. Just like if x plus 2 were a factor, that would give you an x-intercept of negative 2, which is why I'm using negative 2. And for the last one, why I'm using positive 1. So now I just need to evaluate these, and so just grabbing my calculator and putting in 3 for x, and so when I put in 3 for x, I got 8. And so since the remainder then, that's what we found out here, the remainder, that when we divide f of x by x minus 3, the remainder would be 8. Since the remainder is not 0, then that means x minus 3 is not a factor. Do the same thing with negative 2. And when I put that negative 2 in for x, I get negative 12. So same thing, f of negative 2 is not 0, which means that x plus 2 is not a factor. And then x minus 1, let's check f of 1. And that's equal to 0. And so since f of 1 is 0, that means that x minus 1 is a factor. There we go. So just by evaluating our function nicely and quickly, we can test to see whether it's a factor or not. So here we checked whether x minus 3, x plus 2, x minus 1, whether they were factors, and we were able to confirm that x minus 1 is a factor, but the other two were not. All right, follow-up question here, or a related question rather. We have this polynomial and we have a fact. We know that f of 3 is equal to 0, and we want to use that to help us factor our polynomial completely. So the fact that we know is that f of 3, if that's 0, then that means that x minus 3 is a factor. which means that when we divide by x minus 3, we're going to get a remainder of 0, and we can write f of x as x minus 3 times whatever the quotient is. So that's what I'll do now. To factor out x minus 3, I'll divide my polynomial by x minus 3, and I'm using synthetic division to do it. Bringing down my first coefficient, multiplying 3 times 2, adding 3 times 1, adding 3 times negative 3, adding, and this confirms what I expected. F of 3 was 0, and our remainder is 0, so good for us. That means my quotient, 2x squared plus x minus 3. So that means f of x could be written as that factor of x minus 3 times that quotient, 2x squared plus x minus 3. And then to finish factoring it completely, now you can just tackle this. This has reduced it from a less nice less nice cubic function and given us a nicer quadratic function. And this you can factor as we usually do. So here, if I were factoring, I'd look for numbers that multiply to negative 6 and add to positive 1. That would be positive 3 and negative 2. And then just factor by grouping from there on out. And so it factors as x minus 3, 2x plus 3, and x minus 1. So far so good. This has given us a start for things. So if you knew that you had a value of x that made your function equal to 0, then there you go. You could use that to factor your function. Now the question is, how did we come up with that first fact? Here I gave the fact to us that f of 3 was 0. But as you know, there's infinitely many numbers, so you don't want to just start testing random numbers and hoping for the best. We need a way to help guide us to the possible places where our function could be at the x-axis, those possible rational zeros. And that's where the next theorem comes into play, the rational zero theorem. The rational zero theorem gives us a list of possible rational numbers that could be zeros for our polynomial. And these would be it. So any number that's not on our list could not possibly be a rational zero of our polynomial. So basically, this is reducing our workload from having to look at all the possible numbers that exist to just a nicer, shorter list of numbers that might potentially be zeros. A couple of things just to keep in mind here. The first part is the word possible. The rational zero theorem does not tell us which ones actually are zeros or not. That we'll have to still test. But it gives us a list of numbers that might be zeros for our polynomial. The other part, and I'm going to mention this again later on, is that the rational zero theorem doesn't always apply. It applies when we're talking about polynomials and where the polynomials all have integer coefficients, and also where the leading term and the constant term aren't 0. So there's quite a bit in there. That means that there's lots of polynomial functions where the rational zero theorem wouldn't apply. So for example, if I handed you a polynomial like x to the 7 plus x to the 5, that's a polynomial where the constant term is 0, so the rational zero theorem wouldn't apply here. Same sort of thing if I were to hand you a polynomial where a coefficient was not an integer. So something like x to the 7 plus 0.7x plus 3. Because that's not an integer, that means that the rational zero theorem wouldn't apply there either. But let's suppose that we've got a polynomial where the rational zero theorem applies. So its integer coefficients and the leading coefficient, the constant term, none of those are zeros. then that means that if you're looking for a rational number to be a zero of our polynomial, then it would be the numerator, it would be some factor of the constant term, and the denominator would be some factor of the leading coefficient. So as an example here, we've got this polynomial, and it's one where the rational zero theorem would apply. It has only integer coefficients, and the leading coefficient is not 0, it's 9. And the constant term is also not 0, it's 5. And if we're thinking about factors of these numbers, factors of 9 include positive and negative 1, 3, and 9. Those are all the numbers that go into 9. And same thing with 5. You could have plus or minus 1 or plus or minus 5. So possible rational zeros are made by taking one of the factors of the constant term over one of the factors of the leading coefficient. So possible rational zeros includes plus or minus 1 over 1, plus or minus 5 over 1, plus or minus 1 over 3, 5 over 3, plus or minus 1 over 9, and plus or minus 5 over 9. So the rational zero theorem has given us this list of 2, 4, 6, 8, 10, 12 possible rational zeros. So that means that we only have 12 numbers to test, and that's it. So that means anybody who's not on this list automatically could not be a rational zero. So for example, do I need to test whether x minus 2 is a factor? No, I don't. I know that it can't be a factor because 2 is not on my list. How about x minus 3? Well, there's no 3 on my list, so x minus 3 couldn't possibly be a factor. Possibly x minus 1, x plus 1, x minus 5, x plus 5, those sorts of things could be factors of this polynomial, and these are the only possible rational zeros for that polynomial. So if I wanted to now factor this polynomial, I would just have to test those 12 rational zeros, and hopefully one or more of them will turn out to be zeros of my polynomial. And so that's kind of the overall plan here, is that if you have a polynomial that you'd like to factor, and it's got integer coefficients and you're good to go, then first start out with your rational zero theorem, make your list of possible rational zeros, and then the second step, we're going to use the remainder theorem until we find an actual zero of our polynomial. So basically we are going to test these rational zeros until we find one which actually is a zero for our polynomial. And once we know where the zeros are, we can divide out that factor to find our quotient. And once we've done that, that's reduced our degree of our polynomial by 1. We just have to repeat the process, try another 0 and factor it out if you can, try another 0. If it is a 0, then factor it out until we've made our way down through the list and tried all of the zeros, or until we've factored our polynomial, whichever comes first. And that's basically the idea behind any sort of factoring that we'll be doing if it's a larger polynomial. Now, let's go back to this example here where, again, just as a reminder, our list of rational zeros. Courtesy of the rational zero theorem, we had plus or minus 1, plus or minus 5, plus or minus a third, 5/3, 1/9, and 5/9. And so we'd like to tackle this problem of factoring this polynomial. So let's first check. Could 1 be a 0? So let's find out what f of 1 is. And that's negative 32. That's not 0, so that means that x minus 1 is not a factor. Let's do -1. Same thing, putting in -1 for x. And I got that this is also not equal to 0. So that means x plus 1 is not a factor. Let's try +5. And there we go. We have that this is, when I ran this through my calculator, this is equal to 0, which means that x minus 5 is a factor. And so now to factor it out, we're going to take our polynomial f of x and divide it by x minus 5. So we had 9x cubed minus 45x squared minus x plus 5. And we were dividing by x minus 5. And now synthetic division, bringing down, multiplying, adding, multiplying, adding, multiplying, adding, and there we go. As we expected, our remainder is 0. If our remainder didn't turn out to be 0, that would contradict what we just found on the previous slide, that f of 5 was 0. So that would be a sign that something I did was wrong, either my division or evaluating my function. Whatever f of 5 is, that should be the same thing as what I get when I divide by x minus 5. And yes, there we go, our remainder is indeed 0. Our quotient, 9x squared plus 0x minus 1. And so that means f of x is now factored as x minus 5 times that quotient. Now, this would be where we could, if we wanted to, we could continue with the rational zero theorem on this smaller polynomial, 9x squared minus 1, testing it for possible factors. But of course, remember that if you can factor things by hand, there's no need to continue using these theorems. You can certainly just factor by hand. And in this case, 9x squared minus 1, that is a difference of squares, 3x minus 1, 3x plus 1. So I'll factor it that way, and that's where I'll end. I will also give one little side note here, which is you don't always even need to use the rational zero theorem if you happen to notice your polynomial is factorable in another way. If you were to take a look at f of x and think about it just a little bit longer, you might have noticed that f of x actually could have been factored by grouping. You could have factored out 9x squared from the first two terms and a -1 from the last two terms, and got to the same place where I got to by doing all that division. But again, it's not always going to be the case that every polynomial will factor with a nice, clever trick. So this one was one where there is another way to do it. You could factor it by grouping first, but if you didn't notice that, well, you still at least have the rational zero theorem here to help you out.